Right, good evening, everyone. Welcome to you all. Welcome to EGS members and members of the Institute of Mining, Scottish Institute of Mining, whatever. IM3, that seems an odd logo. I can't quite get my head around that, Mark. But anyway, welcome to everybody. Tonight's speaker, Dr. Stephen Hollis. I remember Steve coming to a Highlands workshop in probably about 2008 or thereabouts, which was just when Mark was starting his PhD studies at Southampton University on the subject of tonight's talk, the Tyrone Igneous Complex. It's certainly one of the more enigmatic but probably one of the more significant outcrops, Caledonian outcrops, if you want to call it that, in the UK. And of course, it's sort of doubly interesting because just adjacent to it are some of the gold prospects, which are currently under examination, although some of the exploration is more active than others, shall we say. But it can't be a coincidence that the gold mineralization is right next to this ophiolite. And so Mark has been studying and carrying out, sorry, Mark, I keep mixing you two up. Steve has been researching into the Tyrone Igneous Complex and its complicated geology and its relationship to mineralization, precious metals and others. So it has a major regional geological interest as far as the Caledonian story is concerned, but it has this precious metal interest as well. So for both our audiences, or for all of our audience tonight, I think it's very good that we can hear from somebody who has done a lot of research and is still doing a lot of research. As ever, there are lots of unanswered questions, and you may be able to quiz Steve at the end of tonight's lecture on some of those things that are present in your mind as well. And I'm sure Steve will do his best to answer those. So, Steve, it's our pleasure to welcome you to tell us about the Tyrone Igneous Complex. Cool. It's a long title, so I'm not going to read it out in total.
Thanks, Graham. Hopefully you can all hear me okay. So I should say this work's been going on for quite a number of years now. I started working in this area during my PhD, which started in 2008, as Graham has a good memory, when I went to the Highland workshop for the first time. So I was supervised by Mark Cooper, who many of you might know, has worked at the Northern Irish Survey for quite a number of years. I was supervised by Garth Earls, Richard Harrington, Stephen Roberts down in Southampton. And we kind of published a lot of the PhD research. I then went to Australia and stopped working on this area for obvious reasons of kind of travel and logistics. Did a postdoc in Western Australia working on zinc and lead deposits, hosted in volcanic rocks, very similar setting, but Archean in age. And then when I moved back to Ireland in 2015, I did a postdoc down at University College Dublin, and myself and Mark Cooper, for a few weeks every year, would keep going up to County Tyrone and doing little bits of research. And we still do this every year. We have a week here and there, and we're still trying to answer some of these outstanding kind of questions on how the Grampian formed. Okay, so thanks for the invite, I should say as well. And the talk outline, I'm going to first very briefly introduce the closure of the Iapetus Ocean. You're probably all very familiar with this, but I'm going to focus more on the Grampian phase. So this is the earliest part of the Grampian, the earliest phase of the Caledonian orogeny during the Ordovician. I'll spend the bulk of the talk about the Tyrone Igneous Complex. I'll introduce the various components, how they fit together, and then I'll talk about correlations with equivalent arc and ophiolite sequences in Newfoundland, further along the origin in the Appalachians, and implications for mineralization. And then at the end, I've got 2 slides, and I'm going to kind of wave my arms and speculate about the mineral potential of Ballantrae as well. So I'm not going to cover the connection with the gold deposits at Corrignol, Cavanna Core, but feel free to ask me about that at the end. Okay, so here we have the closure of the Iapetus Ocean. I'm sure you're all familiar. The Iapetus suture runs through the southern part of Scotland, through Ireland, and then it goes off into the Appalachians as the red Indian line. So ultimately, the closure of this ocean brought together Laurentia with Gondwanan affinity crust, so Ganderia avalonia to the south, and Baltica over here as well. So this ocean closure was progressive and it's diachronous. So in the earliest phases, you have essentially subduction, dipping away from the Laurentian margin, and a series of arcs develop from the Late Cambrian through to the Middle Ordovician. And these arcs essentially collide with the Laurentian margin. And this is what causes all the deformation and metamorphism around the Scottish Highlands. You essentially cook up the Dalradian supergroup metasedimentary rocks. And then subsequently in the late Caledonian phase, so Devonian times, you start to collide Avalonia and Baltica with Laurentia. So we're really only interested in this Grampian event. So we're talking late Cambrian through to Middle Ordovician. And I call it event, but it should really be called events, because we have multiple ophiolites of slightly different age, multiple arcs of slightly different age, and outriding microcontinental blocks that basically collide with that continental margin of Laurentia and cause all the deformation and metamorphism through Scotland into Ireland, but then also into northern Newfoundland and in the Appalachian mountain belt as well. Okay, and this is the deformation and metamorphism we're talking about. This is an image from the BGS they got online. And this is the Highland Boundary Fault. And the Highland Boundary Fault, I'm sure you all know it, basically separates the stuff to the south that collided with the Laurentian margin and the stuff to the north, which is essentially the margin sediments that were deformed and metamorphosed. That Highland Boundary Fault you can see here coming through south of Aberdeen to north of Glasgow, indicated by the red line. That continues through the north of Ireland, where locally its surface expression is represented by the Oma thrust. And you can see it through here, and it continues down into North Mayo. So all this stuff through this region, through here, this is essentially bits of terrain, bits of arc, bits of ophiolite, again, that collided with Laurentia between the late Cambrian and the Middle Ordovician. And this is just a diagram showing the pulses of granites across Scotland. You have these older Grampian granites and these newer granites around 400. So this is the Grampian, this is what we're interested in here, not the bulk of the granites and the intrusives across Scotland. Okay, so during this period, here again, we have another geological map. This is obviously Scotland, Ireland, and between these two red lines, this Midland Valley terrain, it's largely concealed, but along the Highland Boundary Fault, you have fragments of ophiolites. You have fragments of ophiolites down here at Ballantrae, in Northern Ireland, in counties Tyrone and Londonderry, and then you have little remnants of bits of Iapetus in North Mayo at Charlestown, and then a really nicely preserved sequence in Western Ireland, where a lot of the classic research was done. So the dating of this deformation and metamorphism is really well constrained. We have a lot of rubidium strontium ages, we have a lot of argon-argon cooling ages, and uranium-lead zircon ages of magmas and intrusive rocks that are basically syn deformational across Western Ireland. So the timing of these accretionary events is really well constrained in most instances between the late Cambrian and Middle Ordovician. So a lot of the early work, particularly in Ireland, was done by Paul Ryan, John Dewey, and then followed on by people like Amy Drought. And they have a really nice sequence in Western Ireland that I'm going to walk you through in a moment, where essentially you have an arc, a juvenile arc, that forms outboard of Laurentia, and it progressively makes its way to the Laurentian margin due to subduction. It collides with the margin, you get lots of syn collisional magmatism, and then you get a subduction flip. So the subduction zone breaks off, the downgoing slab breaks off, and you change the direction, and you start to subduct underneath Laurentia. These other Iapetan fragments, particularly the Tyrone Igneous Complex, was really poorly studied until Mark Cooper started working in the region in about 2008, 2010. The Charlestown group has had a little bit of research, is the Charlestown group through here. And then there's a lot of historic work on Ballantrae and the Highland Border Complex. But the Tyrone complex in particular was really poorly understood, and we didn't really know how it fit in with Western Ireland. Okay, so this is a model from Dave Chu, published 12 years ago now. I remember when this came out. Still seems like quite a new model. Here we have, this is Laurentia, and we have our deposition of our Dalradian supergroup on the Laurentian margin. So essentially what you have is when Iapetus opened, you tore off a load of microcontinental blocks from the margin. And then during the Late Cambrian to Middle Ordovician, you started to recollide these outboard blocks. So in the early instances, you have some really old ophiolites, about 510 million years, the Highland Border Ophiolite, bits of the Deer Park Ophiolite in Western Ireland. It's been proposed were abducted onto these outboard microcontinental blocks. Then what happened is you jammed this subduction zone through here, and subduction stepped back to between the Laurentian margin and these outriding blocks. And this is where we develop our Western Irish arc called the Loch na Fui arc. It's founded on oceanic crust, so it's quite juvenile. And if you look at the geochemical work that Amy Drought did, she shows the progressive geochemical evolution of this arc as it migrates towards the margin, and you get more and more Dalradian metaseds go down the subduction channel and start to contaminate the arc in terms of its geochemistry. This arc then collides with the margin along with its ophiolite, and you start to exhume that into the forearc basin. So they have this really nice model in Western Ireland. They have all the components as you go from the south to the north. You have the arc with bits of potential back arc. You then have a thick forearc basin, which preserves a really nice sedimentary sequence. You then go into a clearly defined ophiolitic backstop, an accretionary prism, blue schists, and then the Laurentian margin itself. So have a really good idea of the way things are dipping and the timing of that accretion. Okay. I'm not going to go through this at length. This is from a paper, a book chapter. It's just come out in the last month by Stuart. And this details not only the evolution of the Loch na Fui system, it summarizes the Tyrone complex, Ballantrae, and everything else. Phil is a co-author on this chapter as well. Essentially what we have here is in the Cambrian, you have a ophiolite formed, a subduction zone ophiolite. It's the one I just showed you. That started to get exhumed sometime around 482 million years ago during the Traumatic. At the same time, you have the formation of what's called the Loch na Fui group. This is the arc that you collide with Laurentia to form all the Dalradian metamorphism. This arc shows a really nice progressive evolution from bonanites through to pholitic basalts, through to calcalkaline basalts and andesites. And then you hit this point through here. These formation names really don't matter, but we have a really good sedimentary record of this is the time, 475 MA. This is when the arc collides, because the arc geochemistry changes to syncollisional felsic volcanism with strongly contaminated geochemistry. As it continues, you get an abundance of metamorphic detritus enters the basin. So we have good timing of when we unroof the origin. And then we have a subduction reversal and a more volcanism dipping under the margin. So we have a really complete record of the Western Irish system. Compared to this, our Northern Irish Tyrone Igneous Complex, we really don't know much about it. So previously, we were trying to tie everything into the Western Irish system, but it's becoming quite clear now our arc is of different age, our ophiolite is of different age, and we don't have this one clear arc and ophiolite that collide with the margin and cause all the deformation. It's a much more complex picture. Okay, so here's the Tyrone Igneous Complex. It's exposed over counties Tyrone and Londonderry and had relatively little academic interest up until the mid-2000s. So there was some early mapping by Hartley. There were some papers by Angus and Cobbing in the 60s. And then Donny Hutton went into the area in the 80s. And this is a difficult time to work in this area. This is during the Troubles. Donny recognized the existence of an ophiolite in the area, published it in Nature, found some graptolites and published that in 1992. But then there was no other work done on this area until about 2008. Western Ireland at this time had probably had about 30, 40 papers published on it. So you can see the level of detail that was missing. There was no geochemistry up to this point, no detailed stratigraphy. There was one zircon age for the entire complex and one graptolite constraint. This is some of the problems that you get when you work in the area. You have huge sand and gravel deposits, a lot of farmland, very little outcrop. So you're trying to match these scrappy exposures all around County Tyrone, hopping from stream section to quarry to bog, and trying to come up with some sort of coherent geological evolution. Then the TELUS project came about. This is a Northern Irish funded survey where they essentially flew a light aircraft over the entire country to produce really high quality geophysical data. So they produced airborne magnetics, electromagnetics, radiometrics, and they also did extensive soil chemistry, stream sediment chemistry, and stream water chemistry. And this is how the PhD came about, because there've been sniffs of mineralization, gold, zinc, lead, copper in this area since the 70s by Rio Finex, NX. And we wanted to see if there was any mineralization and how was that mineralization contained? What was the styles of mineralization? What was the tectonic evolution of the area? And can we use that to better understand where to look for mineral deposits? So the PhD involved lots of field work, lots of geochronology, a whole bunch of geochemistry. And since that time, we've done more age dating. We've done a lot more geochemistry, probably analyzed about 300 rocks from this area, about 60 neodymium isotope analyses, and probably about 20 uranium lead zircon ages using TIMS. So we've really thrown everything at this. Okay, so this is the existing or the pre-existing geological survey of Northern Ireland line work. And I'm going to run you through each of these components in turn. This through here is that Oma thrust that I pointed out earlier. This separates the grey rocks, which are the Dalradian supergroup that host the gold deposits, from all the accreted stuff that formed in the Iapetus Ocean to the south. So these grey rocks, this is the Dalradian supergroup. We're not really interested in that for this talk. We have what's called the Tyrone Central Inlier, and you can see it's here, it's in the central region of the complex. And this is essentially a package of metasedimentary rocks that I'm going to show you is of Dalradian provenance. So this is our outboard microcontinental block that got rifted off the margin and then slammed back into it. This purple stuff through here, I'm going to convince you is an ophiolite.
This blue stuff and these greens, this is all our volcanic arc. This is called the Tyrone Volcanic group, as opposed to the Tyrone Plutonic group. And then we have a suite of late stitching intrusives. These are all these red units through here. These basically pin everything in their present structural position. So you had a basement, the ophiolite comes on over the top, the arc comes over the ophiolite, and then you intrude a load of granites through everything. There's also a weird little granite down here at Tremoge Glen, and I'm going to talk a little bit about that and its significance later on as well. So let's start with the Tyrone Central Inlier. So the work for the Tyrone Central Inlier, this was done by Dave Chew and from Trinity College Dublin, and he showed conclusively this is essentially a sequence of sammites and semi-peelites with green beds, typical that you'd find anywhere across the Scottish Highlands. Its zircon provenance is identical to the Dalradian, but it's essentially been cooked. It's gone up to about 670 degrees and about 6.8 kilobars of pressure. And these metamorphic fabrics are cut by both leucosomes and post-tectonic pegmatites. And Dave Chew did a whole bunch of geochronology and proved all this is Grampian in age. So whatever these metasediments were, they basically had something very hot pushed over the top of them to cook them and deform them during this period, probably an ophiolite. So here are some field photos. I've put in lots of photos of rocks. This is essentially what they look like if you went to this area on a field trip. Great quarry exposures all through this region. You can see the semi-peelites and sammites have a gneisos fabric. You have these cross-cutting pegmatites full of nice muscovite books, tourmaline, K feldspar, and you have abundant melting of these metasedimentary rocks. And you can see this granitic melt, it's stoping its way up to the surface through these deformed metaseds, okay? Let's look at the ophiolite and the arc, because that's where I've done the bulk of my research. So the ophiolite is this sequence in purple through here. It's called the Tyrone Plutonic group. Donny Hutton originally did a lot of work on this area in the 80s, and he first recognized this was an ophiolite. He had the classic zones. You have the layered gabbros, pegmatitic gabbros through the sheeted dike complex, through here in this dashed horizontal lines. And then you see bits of pillow lavas, okay? So Donny thought you could map out this systematic zonation with the ophiolite. Not quite true, because when we look at the TELUS data, this is an electromagnetics map, and this is magnetics. And you can see here the ophiolite is these dark purple slabs. Essentially, it's been tectonically imbricated as it's been thrust over the basement during the Grampian, and we have slices of slightly different potential age. So we have some bits of ophiolite through here at Black Rock, between these two black bars. We've dated to around 484 million years. We have bits of ophiolite, this main slab through here, we call the scalp slice. That's about 480 million years old. And then we have this slab through here, around Orator Quarry. And we don't really know the age of this at the present time, but it's probably a similar age. Through this central region, between these two black lines, this is all meant to be Tyrone Central Inlier. But you can see from the magnetics map, it's actually underlain by slices of ophiolite. So this is probably some sort of southeast directed thrusting related to when the Dalradian came over the top, and you've cut down into the underlying stratigraphy, and you've had some sort of duplication underneath. What does the ophiolite look like? Well, these are some pegmatitic gabbros, beautiful exposures of this stuff. We've ran loads of field trips here. You can see the nice coarse amphibole crystals. You see sheeted dikes intruded by gabbros, and they themselves have intruded gabbros. We've now discovered the ultramafic rocks in the last couple of years around Orator Quarry, serpentinite pods with pyroxenite and so on. The sheeted dikes have been discovered to contain copper mineralization, little bit. We'll get onto that later. But in terms of the geochemistry, this ophiolite's exactly like Ballantrae. It's like the Shetland ophiolite. It's like the Highland border ophiolite. It's the same kind of geochemistry. It's a subduction zone ophiolite. Here we have some nice other field photographs. This is the scale of the amphibole in some of these pegmatitic gabbros. And we've seen in recent years, these are sheared pegmatite felsic intrusive sheets that are deformed, that cross-cut the ophiolite itself. So this is something we're actually in the process of trying to date. What do we get at the base of the ophiolite? Well, we see lots and lots of melting between the contact between our ophiolite and our metamorphic basement. That's the Tyrone Central Inlier. We see abundant melting, syndeformational melting. You can see all this granitic tonalitic material through here. It's deformed, it's folded. Some of it cross-cuts the main fabrics. We get lovely, large, rotated amphibole porphyroblasts. And this is evidence that essentially you've pushed a hot ophiolite over the top of that outriding sequence of met-sedimentary rocks. This exposure was about that big. We stumbled across it. We had to pull all the trees off it, all the shrubs, all the grass, and then we went in with a power washer to find this. It's very difficult to find nice exposures in this area. So if you find one, you've got to really put the work in. This is in the middle of a forest as well. We had to go through a forest track with a car full of water as well. This is some photos from last year, Evishbrack Mountain. Again, as we approach the contact between the ophiolite and the basement, we see lots and lots of evidence of melting of those basement rocks. You can see here, these are blocks of diorite. You've got bits of gabbro that's been myelinatized and sheared and is intruded with melt. So this is something we're actually trying to date. We're trying to date some of this syndeformational melt and some of these cross-cutting sheets to try and pin down the exact timing of when this occurred. Can we actually say something about when the abduction itself occurred? So I think we can. That granite I pointed out earlier, that is an S-type granite or a muscovite-bearing granite. It's one of very few in the area, and they only generally form from the melting of sedimentary rocks. And we've dated this granite. It's a large granite. It's been quarried at Tremoge Glen, and it's produced an age of 477 million years. This is just after the age of our ophiolite. So ophiolites tend to form and then they get abducted really quick. So we think this 477 MA, this is dating the timing of our ophiolites, coming over that outriding block, gets all that melt going, as I showed you in the last photos. It collects and forms all these S-type granites. Importantly, these granites contain zircons, inherited zircons, that are basically the same as the underlying Tyrone Central Inlier. So again, it's good evidence that you've melted that material during this ophiolite abduction. These dikes you can see through here, these cross-cut the fabric in the granite and have a unique geochemistry that's completely different to the ophiolite, but is in fact identical to the arc, which forms 5 million years later. So these are actually feeder veins to the later arc that comes over the top of this entire sequence. This is the said arc. It's called the Tyrone Volcanic Group. It's a real mixed bag. Again, lots of different rocks in the area. We have nice rhyolites with tonalite clasts, massive basaltic flows, pillow lavas, layered cherts, black shales. This is a calc-alkaline arc. It's different geochemistry to the ophiolite. It's very easy to distinguish. We've remapped it. We've identified 5 main formations. We have some stuff down here in the south, which looks more like a juvenile arc, some stuff to the north, which looks more evolved, and some stuff through here in the Beckmore formation that looks more like a classic back arc, okay? Different geochemistry to all these different formations. And this arc was extremely short-lived. So remember I showed you earlier that Western Irish arc, it got going about 490 million years ago, and then it ran through to about 464 million years ago. Our arc formed at 473, and it was all over by 469. So this is a very short-lived arc, and we do not have that nice progressive geochemical evolution through the arc sequence. We have a good constraints for the timing of the onset of the arc. We have inherited zircons, we have the first oldest intrusions coming through at 473. We have plagiogranites, we have diorites, calcalkaline andesites dated from down here. The upper part all gives these similar ages, 473 to 469. And then I should point out that the arc continues under the Omophrost, underneath the gold deposits, and we don't know the northern extent. We know it continues because the mining company has drilled through the Omophrost, and we've seen the nature of the volcanics underneath. So we have some unpublished zircon ages that me and Mark are writing up at the moment. So this arc, although it's very short-lived, has a very complex 4 million year history, as indicated by this rather complex cartoon here. And essentially what we have is intermittent, disorganized intra-arc rifting. So that basically means your arc, you keep pulling it apart during periods of extension. So you have normal calcalkaline lava flows, but then intermittently between those calcalkaline flows, you have a bunch of oib basalts or emorb basalts that don't have an arc signature. And these are really typical of rift-related basalts in modern arc systems, such as the Isotope arc, and other examples where you get rift tips that propagate in back arc environments, and you get these iron, titanium, phosphorus enriched morbs and oibs. Okay, so we see several occurrences all the way through the arc, lots and lots of evidence for arc rifting. And there's a reason why I talk about this, because it's really important for mineralization. We'll come on to that in a short while. Also at these horizons where you get these rift basalts, you get lots of ironstones, you get lots of hydrothermal alteration, and we're talking kilometer scale hydrothermal alteration. So typical you get on the seafloor. And we get lots and lots of sniffs of copper, zinc, lead, gold, and silver mineralization. And it's associated with these periods when you get this extension in the arc system. Okay. And for those of you who are interested in geochemistry, this is neodymium data. This is our normal arc through here, the calcalkaline lavas, contaminated signatures, and these are our rift basalts. They're more juvenile. We don't see this in Western Ireland, neither do we see the zinc, lead, copper mineralization in Western Ireland, because the rifting is a fundamental criteria to form volcanogenic massive sulfide deposits that I'll come to in a couple of slides' time. Okay, so we've got our outriding metamorphic block, the Tyrone Central Inlier. We've plopped a young ophiolite over the top, started to melt it, form S-type granites. We've then formed a relatively young arc, pulled it apart and pushed that over the top of both. And then we get what's called the late intrusive suite. So these occur from 470 to around 464 million years. We have a lot of ages for these, and we can show really nicely how you go from the diorites through the biotite granites, through the granites into the quartz porphyries. And all of these, importantly, contain inherited zircons derived from, you guessed it, the underlying Tyrone Central Inlier. So these intrusions have come through everything, and you can see some of them intrude the ophiolite, some of them intrude the basement, some of them intrude the arc in the basement, and so on. So they basically come through everything. So that gives us a timing of our final accretion. The last one, 464, is just before orogenic peak orogenesis ends. You get orogenic collapse, and you get the gold mineralization at Corignault. Okay, so this formation of this arc ophiolite complex is not only important for the the zinc and the copper and the lead that it potentially contained, but also the timing of the gold mineralization in the Dalradian supergroup. Okay, so putting it all together, this is a summary diagram. This is a slightly more complex one that's in the recent book chapter, but essentially you have an ophiolite that forms during the traumatic. You then abduct it, start to get some melting and S-type granite formations. Then our volcanic arc starts to form in the Middle Orogeny. You get lots of mafic lavas, lots of felsic lavas, pretty much at the same time. How I envisage this is you have some back arcs, inter-arc basins, and so on. Lots of different magma suites. You accrete that at around 470, which is when all the tonalites come in. And then all these intrusions essentially stitch everything together. And this is the timing of the deformation metamorphism in the Tyrone Central Inlier. So this is the basement. So all this timing fits together really quite nicely now. How does this compare to Western Ireland before I get onto the mineralization? Well, you remember we have our ophiolite down here at 514 million years. Here's our ophiolite sitting at about 482. So it's clearly much younger ophiolite. While their ophiolite is getting exhumed, we see lots of detrital chrome in the Letterbrock formation at 480. This is when ours is only start to form. So there's clear diachronous accretion going on along this orogenic belt. It's not a simple picture as we first envisaged from Western Ireland. Our arc volcanism, while they have syn-collisional volcanism during the upper Orogeny, the lower Llanvern, this is where we get to start see our intra-arc rifting. So again, different processes are happening in Western Ireland to Northern Ireland, further east along the Laurentia margin at this time. And then our continental intrusives come through around a similar time. So this is probably subduction flip that's happening around about the same period. So it's not a case of there was one arc, one ophiolite in the Grampian that basically collided with the margin. We have multiple arcs, multiple ophiolites, and this is exactly what they see in Newfoundland. Okay, and we'll come on to Newfoundland in a little moment. So I mentioned these arc lavas, there you get lots of pillow basalt, you get lots of ironstones, black shales. This is all submarine volcanism, right? We get lots of extension. Submarine arc environments undergoing extension are the perfect formation environment for something called volcanogenic massive sulfide deposits, or VMS deposits. And these are essentially ore bodies that we mine in the rock record from the Archean. Here's an Archean mine deposit, Jaguar from Western Australia. And this is a modern example forming on the seafloor at the present time. Okay, these are black smoker systems. So these are the exact same deposit types we're talking about. You have an extensional environment. You start to move a lot of water around in basaltic crust, strip metals out of rocks, bring them back to the seafloor and precipitate out your massive sulfide ore bodies. These deposit types are mined globally for copper, zinc, lead, gold, and silver. But in recent years, we've identified they can also contain appreciable quantities of certain critical metals used in green technologies. So although cobalt is used in lithium cobalt batteries, some VMS deposits contain appreciable and extractable quantities of cobalt. Other ones can be enriched in antimony, bismuth, tellurium. Tellurium goes into solar panels and so on. So there's a big push at the moment. The BGS created the Critical Metal Intelligence Centre to try and see what the UK has in terms of mineral deposit types, things that might be extractable, and also what critical metals they might contain. So I'm going to put it to you that Tyrone is highly prospective for VMS deposits and could contain critical metals as well. So this is an ingredients list for how you form a VMS deposit. You need a submarine setting because you need lots of seawater. You need extension to get that seawater down and through fracture zones, through faults. Your rifting also allows lots of magmatism close to the surface. And that magmatism in the shape of subvolcanic intrusions drives hydrothermal circulation or convection in the shallow parts of the crust. You strip all your metals out down here above your magma chambers, and your metal-rich hydrothermal fluids, 300 degrees, pH of about 4, full of hydrogen sulfide, they go up back towards the seafloor, and it mixes with seawater. And it's the mixing with seawater, the pH change, and the temperature change that dumps out all the copper sulfides, the zinc sulfides, the lead sulfides at the seafloor, okay? So this is what you need, and this is exactly what we have in County Tyrone. One thing that's key to VMS deposits is the favorable horizon. So normally in a VMS camp, there's one particular time period, the Goldilocks time period, where everything is just right to form world-class or mineable ore bodies, okay? So you've got to have a really good understanding of your volcanic stratigraphy, particularly along strike. Volcanic rocks are very hard to correlate along strike. And you've got to know which is the best formation where you're going to find all these ore bodies. So what makes me so confident we're going to find ore bodies? Well, if you go along the origin and you go along, this is the Red Indian line, or the Iapetus Ocean in Newfoundland, and it continues through here, through Quebec. Both on the northern side of Iapetus and on the southern side, you have a lot of VMS deposits, both in Newfoundland, Quebec, New Brunswick. The ones in Newfoundland at Buckens are the most metal-rich VMS deposits in the world. And the ones at New Brunswick on the southern side are some of the largest tonnage VMS deposits in the world, okay? So there's 68 of these alone in Newfoundland. And the metal flavor, so what you get, if you get a bit of copper, a bit of lead, a bit of zinc, depends on the nature of the volcanic rocks, the tectonic setting, and so on. So there's a lot of intricacies. There's lots of different deposit types for VMS, different ways to classify them, but you can ultimately predict what types of deposits you might get in your area. This is a model for the Grampian or tectonic origin in Newfoundland. You have these outriding microcontinental blocks that you've abducted some early ophiolites onto. You've then stepped back subduction and you formed an arc through here, similar to Western Ireland. You've then collided your block to the margin, and then you form late arcs and ophiolites from about 480 to around 455 million years. In all of these arcs and in all of these ophiolites in Newfoundland, they get VMS deposits that are economic to extract. These are the ones at Buckens, these green triangles. They have the highest concentration of metals and variable tonnages. But these things have been mined and they're world-class deposits. The Buckens deposits, or the Buckens-Roberts arc, is basically part of the Aniopscotch accretionary tract, which I'm going to show you is a dead ringer for the Tyrone Igneous Complex. So here are some broad comparisons between the Tyrone Igneous Complex and the Aniopscotch accretionary tract. You have an outboard block in both cases, dashwoods, they have dashwoods. We have the Tyrone Central Inlier, we need a better name for it. We have an ophiolite, it's of similar age, almost identical age when you consider their errors. We have bits of preserved mantle rocks, but mostly it's the upper parts of the ophiolite. The timing of the ophiolite accretion, we think it's 477. Theirs is sometime after 478, but before 473. The volcanic arc, they have and we have same age, or, you know, near enough. And in terms of the geochemistry, the basalts, the rhyolites, it's exactly the same. The timing of the accretion of that ophiolite, and the arc, is near identical. They have stitching tonalites that come through around 470. Hornblende and biotite granites the same time. And then they get lots and lots of mineral deposits that they can mine. So where are our mineral deposits? So where are we going to look? The easiest thing is to see what they did and to copy it. So they have a bunch of different formations in Newfoundland. And we basically, I went to work for the exploration company during my PhD, and we tried to make some equivalencies between our rocks and their rocks. So their Buckens River formation that has all the good VMS deposits, that's very similar in terms of age, geochemistry, the nature of the rocks, to our so-called Greencastle formation. And I'll show you that on the next slide where the Greencastle formation is. We have stuff that's more like a back arc. They have stuff that's more like a back arc. They have stuff that's more like a juvenile arc, and so do we. But we're really interested in this Greencastle formation. In 2011, 2012, there were a bunch of Canadian prospectors came over. This is Dan Moss. You saw him earlier, stood in front of that sand and gravel pit. And they essentially prospected the Greencastle formation. That's this pale blue unit through here. And the Brock-Derg formation, which is the overlying one, to see if they could find any mineralization. And prospecting is a completely different set of skills to geology. They're like basset hounds. If there's some sulfide, they'll sniff it out. And within about a month, they found lots and lots of mineralization in outcrop and also in float, but mostly in outcrop. So this is Cashel Burn, 3.5 grams a ton gold, 4.3% base metal. The nearest outcrop to this is about 1 kilometer away, very poorly exposed area. Crush up to 24 grams per ton in silicified rhyolite at the surface. Nearby rhyolites also run anomalous gold, but then again, there's large amounts of cover. Gold at Reculpa, base metals also at Crush, massive pyrite discovered at 4 mil, so on and so on. This is really prospective for VMS type deposits. I should mention the hydrothermal alteration we see here is a dead ringer for the Canadian VMS systems. And you can go from stream section to stream section that are hundreds of meters apart, and it's essentially the same hydrothermal system. So this isn't just a little bit of hydrothermal fluid that's coming up, creating a little bit of pyrite, a little bit of sphalerite here and there. These are big systems that we're talking about. But we're talking about a needle in a haystack. What I've done here is I've superimposed the Buckens deposits on our map of the Tyrone complex, which are these black blobs. And remember, we have about less than 5% exposure. And these ore bodies could be at any depth. They could be at 200 meters, 400 meters at the surface. We really don't know, okay? So this area is incredibly prospective. We wrote about this in 2016 in a book where we go through some of the geophysical anomalies, soil anomalies associated with this. After I got back from Australia, we've been doing some more field trips in the area. We took the Southampton student group from the Society of Economic Geology group chapter to Tyrone. As we were going around one of the new exposures, carved into a rhyolite on the side of the hill, found lots and lots of copper mineralization. Just didn't know this was here. This is big sample. It's in my office, about that big. Quartz vein material shot through with pyrite, chalcopyrite, chlorite, and magnetite. This is some stuff we found in the metamorphic basement. Pyrite with quartz, chalcopyrite, and some critical metal minerals as well. This is some work by Walkabout Resources, who had one of the licenses until fairly recently. 2018, they announced they'd got sniffs of cobalt mineralization within the area, within one of these quarries. You can see it here. It's right in the corner of the quarry. You can see the nature of the exposure you're dealing with nearby. If you've not got a stream or you've got a quarry, it's very difficult to work out what is underneath your feet. There was some bismuth sulfur salts, silver tellurides discovered recently. There's high tellurium in soils over some of these tonalite intrusions, and there's known copper and gold associated with other tonalite intrusions. So we have multiple styles of mineralization. We have potential base metal deposits, and some of these could be enriched in critical metals as well.
Okay, so closer to home, only a couple more slides. I'm going to wave my arms a little bit about Ballantrae. We started looking at Ballantrae in recent years. Phil took me and Mark there on a field trip years ago with Richard Harrington. And it kind of piqued our interest because we could see that although the arc at Ballantrae is a little bit more juvenile, we have a lot of the same characteristics. So the Ballantrae, the ophiolite itself, so you have the northern and southern serpentinite belts, and then between them lots and lots of structurally bound bits of volcanic arc, back arc within plate lavas. But the ophiolite itself has a similar age again to in Tyrone. Ages of 483 plus or minus 4, and then around 487 with a bigger error, okay? I think this is an potassium argon age. It was abducted at 477, exactly like our ophiolite. This is a really nice new age using garnet geochronology, unless I'm mistaken. The arc lavas themselves, some of these are predominantly morb-like, other ones are island arc foliites, other ones are more calc-alkaline, but you can see they're largely tectonically dissected into distinct packages. We really don't see this that much in Tyrone. We have quite a nice complete arc sequence where we see this stuff more interbedded. But in terms of the range of magma affinities, we see very similar stuff in Tyrone to in Ballantrae. We also see these within plate basalts. This is the E-morb, oib-like rift basalts we see in Tyrone. The actual arc volcanics themselves are similar to Tyrone again. They're orogenic to Clanverne potentially, but the main difference is the arc is more juvenile. This does not disqualify us for VMS deposits, but it just means our VMS deposits, if they occur at Ballantrae, are going to be so-called Abitibi type or Cypress types. They're going to be more copper rich and zinc copper rich, as opposed to polymetallic, lead, zinc, copper, gold, silver. So it's due to the different nature of the footwall rocks you're ultimately leaching. We had a little student project back in 2022, last year in the summer. A geoenergy student, Patrick Brown, I went down with him to a few days mapping around Ben A. Lee. This is Phil, Richard Harrington, and that's me with a hammer back in 2014 when we first went to this area. You can see the copper staining on this rock on the beach section, black cherts full of copper mineralization, some of the hydrothermally altered tuffs, diorite intrusions, also have VMS style alteration, and there's plenty of copper knocking around. We couldn't actually tell if the mineralization here at Ben A. Lee was similar VMS style or it's just copper moving around some late fault zones. More work to be done on that point. But there's no reason why the Ballantrae Ophiolite Complex shouldn't also be prospective for these seafloor type styles of mineralization. A friend of mine, Matt Mawson, used to work for Walkabout. He came here as part of his master's thesis, looking at critical metal deportments in ophiolites, and he found other areas of copper mineralization elsewhere to at Ben A. Lee, up at Ben A. Head, and I think at Pinbane as well. So there's good potential again at Ballantrae, but it's this arc rifting that's so important. You don't get this style of mineralization in Western Ireland because you lack that seafloor extension. Okay, so last slide. What about the south of the Iapetus Ocean? I should mention it. There are mine deposits at Paris Mountain in Anglesey. If you get the ferry over to Dublin, you'll drive past some of the mines nearby on your way. These have been mined for centuries. I'm a bit of a coin collector, so I have these coins. These are Conda tokens, so half penny and penny tokens back in the 1800s. When the Royal Mint wasn't circulating enough low denomination currency, the mines actually started producing their own copper coinage. So back in the 1800s, 1700s, when these mines were active, the copper that was produced was it pretty much in everyone's pocket, both in the UK and in Ireland. But these deposits don't occur in isolation. They're normally stacked. They occur at favorable time horizons. You have cyclicity of volcanism. So it's very unlikely that the mine deposit at Paris Mountain is it. And it's also likely there's future deposits around Avoca. And there's some exploration companies looking at that at the moment. And last statement of the talk, if we can secure our commodities in Europe in an environmentally friendly way, we really should do so. And I'll leave it there. Cool. Thanks very much.
Everything.